All right, let's continue looking at evaluating some definite integrals using our limit definition. So number 2, last time we did a constant. This time we're going to do a linear function. And so we have the definite integral from -1 to 2 of 2x dx. All right, so again, let's assume equal widths. Right, so technically the Riemann sum, the general form says the width of the largest subinterval goes to 0. We can, again, by the asterisks up above here, we're going to assume equal widths. And so we're going to go back to the case that we really used in the previous section. And so we're going to look at this by evaluating the limit as n goes to infinity of the sum as I goes from 1 to n of, in this case, my function is 2, and then I'm going to need representation for the u sub I, and then also my delta x here. So my change in x is the b minus a over n, excuse me, so 3 over m. All right, so the u sub I, or the c sub I, is what we used last time in the last section. So the u sub I, or what we used last time, the c sub I, this is where we found, through looking at the arbitrary representation of both left endpoints and right endpoints, we found that using the right endpoints was actually easier, the notation, and so that ended up being the a plus I delta x. A in this case is the -1 plus I times, and our delta x is what we just were computing up here, the 2 minus -1, so 2 plus 1, so 3 over n. And so we end up with -1 plus 3 over n times I. All right, so that's our representation that we're going to use here. So -1 plus 3 over n I. I'm going to put this in parentheses. All right, so let's continue here. So we have our limit as n goes to infinity. Let's bring the delta x, the 3 over n, out in front of the sum. So sum as I goes from 1 to n of the -2 plus 6 over n I. So just distributing through the 2, or honestly I could have just factored that 2 out in front of the sum as well. I just sort of jumped in and distributed either way. So remember that we have properties of sums that say we can essentially take our sum here term by term. So the sum as I goes from 1 to n of -2 plus the sum as I goes from 1 to n of 6 over n I. And again, just like I did with the 3 over n brought that in front of the whole initial sum, we can also think about bringing this 6 over n just in front of that second sum, because again, the 6 over n is really like a constant multiple. There's not an I, which is the index. There's no I in that, so that multiple can just come in front. All right, and then with our sum formulas, the sum of a constant is that constant times n. The sum as I goes from 1 to n of I is the n times the n plus 1 all over 2. And so here's where we're at. We still need to distribute through this 3 over n, and then we will need to take the limit. So we have our limit as n goes to infinity of negative 6n over n plus 18n times n plus 1 all over 2n squared. And again, when degree of numerator is equal to degree of denominator, in this case, if you want to even just think of reducing the n over n, you can, but this is going to go to negative 6. The second term, this is really like 18n squared plus 18n. Again, when the degrees are equal, that limit going to infinity is the ratio of the lead coefficients. So the 18 over the 2, which is 9. And so we end up with 3. So the definite integral from negative 1 to 2, as defined as this limit of the Riemann sum, is equal to 3. All right, now let's make some observations. I did a linear example. I want us to sketch this region. So number 3, let's sketch, just shorthand here, I'll say let's sketch number 2. All right, so what are we looking at? We were looking at the function f of x equals 2x. So let's say something roughly like this. And we are going from negative 1 to 2. So let's say this is over here, negative 1. We'll say this is at 2. And so here's what we have. And so this is the first time as we've sketched something that I've given us anything where we're looking at a region that is both above, as in this portion, and below the x-axis. So if we kind of think about this little region right in here, that region is below the x-axis. All right, well, let's think about, the idea of area. We've done a linear example before, and we just basically, we added up, some geometric regions, a triangle and a rectangle, and we added them up, and that's what we saw in the last section. But this is a little different, right? Okay, so, but let's figure out what these areas are. So in the first one right here, if I sub in 2 into the function, remember this is y equals 2x. So 2 times 2 is 4, and then down here, subbing in negative 1. So this is the point negative 1, 2. So if we compute this area, so 1/2 base, which is 2, so half of 2 is 1, times the height, which is 4. So 1 times 4 is 4. So that's the area of that region. And then 1/2 base times height, so base is, let's say 1, times the height is 2, so half of 1 times 2 is just going to be 1. Okay, so if I notice, here's the regions that we have, and so I want us just to make a hypothesis based on this sketch. So could we come up with maybe, and then talk about why that's the case, a hypothesis about the relationship that we're seeing here, the relationship between the definite integral and the area when there are regions that are below the x-axis. So up until now, we've only seen some examples where the area was above the x-axis. This is the first time where we're really focusing on something where there are some regions also below the x-axis. So if I know that my result is supposed to get me to 3, my hypothesis here, I'm looking at the relationship of the areas of 4 and 1. And so I'm kind of thinking that as I look at this definite integral from negative 1 to 0 of 2x dx, and I know that that comes out to be 3. Hang on just a second, I need to close my window. because somebody is mowing. Hold on, sorry. Sorry about this. I don't know if the mic picked up on it, but there was very loud mowers right outside my window right here. Okay, so if I'm trying to make this hypothesis, I know from number 2, I know this comes out to be 3, and I know that it has to do with relationships with these areas, and so it's kind of looking a bit like, well, it's definitely not 1 plus 4, but what it definitely would be is it would equal 4 minus 1. So 4 is the area of the region that was above the x-axis, minus, and 1 is the area of the region that is below the x-axis. So that seems like a pretty reasonable hypothesis just based on this example that we were looking at here. So, and in fact that's the case. So let's just talk about this geometric interpretation of our definite integral. Now, when the region is above the x-axis, this is exactly what we've been talking about all along. If we have a region that is above and we are going to talk about finding the area, then that is going to be the definite integral from a to b. We'll rewrite that as, again, that limit of that sum, and that's going to give us the actual area. Now, what we just saw was a situation, so that was when the region was above the x-axis. So what we just saw in this last example is if the region was below the x-axis. So when it's above, we're all good, right? When it is below, our little hypothesis from the last example is we are going to get the negative of that area. So we end up getting negative that area. So let's think about why that negative is occurring here. And so let's think about the definition again of our definite integral from a to b of f of x dx. Assuming the equal widths case, it's the limit as n goes to infinity of the sum as I goes from 1 to n of the f of either c sub I or u sub I times delta x. So again, here I'm assuming equal widths just for ease of our conversation. All right, so let's think about if you were to draw in some rectangles here, those f of c sub i's. So let's say I was using, breaking up my interval here, and I get a few sub-intervals, maybe some rectangles. And then, I don't know, let's say I'm using my left endpoints, so there's f of a, here's f of x sub 1, f of x sub 2, and so on. So what happens, of course, is that all of these, so these are all of my f of c sub i's. These are all below the x-axis. And so all of these, I have a sum here of a bunch of f of c sub i's that are all going to be below the x-axis. So they are all going to be negative. And so if you sum a negative, you're going to get a negative. And then that negative can be brought out in front of the whole thing. And so what you end up with is, we would bring that negative out in front. Negative can just get carried along here. And then what we really have is negative the limits of our sum. And so it just becomes the sum, of course, of all those, partitions, the width times all those various f of c sub i's. But this is why we end up with negative of that area. So this negative, summing a bunch of negatives gives us a negative, and then we end up with negative of that area. All right, so that's the idea here. And now if we were to put it all together, and if we have a combination of regions that are above and below the x-axis, so let's say I just called this region right in here, we'll say that this little sliver right there, we'll say that that's capital A, capital B, capital C, that little part here we'll call capital D, and capital E. And so if we were to look at the definite integral from lowercase a to lowercase b of f of x dx. All right, so by definition, we could break it up into, looking at it from, like, let's say a to that first little x1, and maybe from x1 to x2. We could break it up here. And what we would really end up with when we would be done is we would have, all right, well, the first region, it would be the area, that area A. But then the second portion, because it's negative, would be minus whatever the area of B is. And then the next part would be positive, the area of C. The next little integral below the x-axis, so minus the D. And then the last part would be plus the E. So what we end up with, if we just reordered our terms, we would have the A plus C plus E, and then factoring out the negative from both the B and the D, what we really end up with here is that area that is above the x-axis, so the sum of the A, the C, and the E. So the sum of all of the areas, area that is above the x-axis, and then minus the area that is below the x-axis. All right, so basically what do we have? We have this definite integral, which is the sum of the areas of the rectangles, as long as all of those are above the x-axis. If they're below the x-axis, the f of c sub i's all become negative, so we get the negative of that area. And then if we get a region that has both, so in general, if we get into an integral that has some regions that are both above and below the x-axis, then the geometric interpretation is going to be the difference between the area that's above and then minus the area that is below. So let's just take a second to pause and realize what we have at this point. So we have defined this definite integral from a to b of f of x dx as the limit of the Riemann sum, essentially. The Riemann sum in general says let the width of the largest partition go to 0, but we can assume equal widths case, and then we can just go back to saying let n go to infinity. So one way to evaluate a definite integral is using that limit definition. The other way is to use some basic geometry. So we'll come back next time and we'll end this section with just a couple more examples, kind of recapping where we're at before we go on to the next section.